Has anyone ever given you a shape and asked you to draw it without taking your pen off the paper? Perhaps when you see something like this, your natural reaction is to get stuck in and give it a go. But this can be frustrating. You feel like there should be a way to do it, but you can't be sure.
Hi, I'm Beth, and today we're going to talk about what shapes you can draw without taking your pen off the paper. For some shapes, it's pretty clear that you can draw them in this way.
Take a square, for instance. If I put my pen here and draw like this, we can draw the square, no problem. Shapes like this that we can draw without taking our pen off the paper are called traversible. And we can also see that with this shape here, I could have started from any of the dots and I still would have been able to draw the square. How about this shape? If I put my pen here and draw like this, so I'm not allowed to go back over the same line twice, so I'm now stuck here. So I haven't successfully drawn this shape. But could I have gone a different route? Let's try start off the same. So I went along here. So instead of going up there, I could have gone up here. But then I have to go down here, and again I'm stuck. Let's try again starting from the same point and do something different again. I have to go down here, right, and then I'm not going to be able to do both of these. I can just choose one because I can't go back along where I've already drawn. So again, I'm stuck and haven't successfully drawn this shape. So I'm pretty confident I can't draw this shape starting from this point here. But what about if I started from a different point? Well, in fact, this shape is rotationally symmetric. So that means that if you imagine starting at this point, if you actually sort of rotated this shape like this, then it's actually equivalent to starting at this point. So if I can't draw this shape starting from this point, I won't be able to draw it starting from this point either. So it looks like to me that we can't draw this shape wherever we start from. So I think this shape is not traversible. How about this shape? Let's dive in and give it a go. Uh-oh, it looks like I'm going to be stuck. I can't do this side as well. So that didn't work. Let's give it another go. So I'm going to start from the same place here. And let's see if I could have done something different. So let's go along this edge I missed before first. Where should I go? Let's go up here, around here, like this. And once again, I can't complete it. That's the best I can do. What about if I try a different vertex? Let's say we start from here. So let's go up and around like this. Oh, this is looking good. Right, so I can draw this shape. So this shape is traversible. But I think I have to be a bit careful because it looked like I couldn't do it from this dot, but I definitely could do it starting from this dot. So possibly we need to be careful about where we start.
So whilst we made some progress using trial and error, I think we can all agree it's perhaps not the best method to test if we can draw a shape without taking our pen off the paper. For instance, that last shape looked like we couldn't draw it at all, but actually we could. So what's going on? Is there a better way to tell if a shape is traversible? And can we tell beforehand which dot we should start at, or if it doesn't matter? Let's take a brief segue to some terminology.
These shapes that we're drawing are in fact called graphs. Graphs are just a bunch of dots and some lines joining them. The dots on our shapes, or graphs, are called vertices. Every vertex in a graph has something called a degree. This is the number of lines sticking out of the vertex. So this vertex has got 3 lines coming out of it, so it has degree 3. Whereas this vertex has 1, 2, 3, 4 lines coming out of it, so it has degree 4. Let's label the degrees of each of the vertices on our 3 graphs. Does this help our investigation?
Let's come back to these graphs in a moment, as I want to think about what actually happens when we trace our pen along a shape, or what we now call a graph.
Let's pretend we're trying to draw a general graph, so I don't mind what it looks like. In every drawing attempt, we're going to start at a vertex, or a dot, so let's say we're starting here. Then what we do next is we leave it by going along a line to another vertex, let's say over here. Note that by leaving this vertex and going to another one, we've added 1 to the degree of this vertex. This vertex now has degree 1. Now what do we do once we've reached this vertex? Well, we leave it again and go to a different vertex. So let's say we're leaving it and going up to another vertex over here somewhere. So we've gone this direction. Note by entering and then leaving this vertex, we add 2 lines coming out of this vertex. So this vertex now has degree 2. So now we're here, let's go to another vertex on our graph. So say we're going over this way. And note the same thing has happened. By entering and leaving this vertex, we add 2 to its degree. So we keep doing this. Every time we enter and then leave a vertex, we're adding 2 to its degree. So say next up in our graph, we return to a previous vertex. Let's say we're going back to this one. So we've added 2 here to the degree, and then we're about to add 2 to this degree again. So this is going to have degree 4 once we leave it. Let's say we go over here. We can also return back to our starting point. So let's say the next place on our journey is through this vertex. And let's say we come down here. How do we finish up when we're drawing a shape? Well, we either end up back at the vertex where we started, like in our square example, we ended up back where we started, or we end up at a different vertex. That happened in our third example. So first let's consider the case where we've almost finished drawing our shape, and to finish it we need to end up back where we started. So we're doing our final line over here, and we've finished drawing our shape by ending up back where we started. Now let's think about the total degree of each vertex in this graph. This starting vertex has degree 4. This one's got degree 1, 2, 3, 4. Drawn a 3. There we go, 4. This one's got degree 2. And actually we notice they're all even degrees. We haven't had any odd degrees on our journey. Now let's think, does this make sense? Let's ignore the starting vertex for a moment. Every other vertex, every time we go in and out of it, we add 2 to the degree. 2 plus 2 plus 2, however many times, is always going to be even. Now what about this starting vertex? Well, it started off with odd degree. It started off with degree 1. But then every time we entered and left it, we added 2 to its degree. So here we added 2 by going in and out of it. So currently we're on 1 plus 2, and then we can keep entering and leaving the vertex, so plus 2 plus 2 plus 2, so on. But then at the very end, we come back to where we started. So that adds 1 again to the degree of the starting vertex. And so that will give us an even number always. Furthermore, we can see that in this case where we end up back where we started, we've sort of formed like a giant loop of this graph. So we could keep repeating and repeating drawing this graph over and over again because we end up back where we started. And that actually also means we could start from any vertex and be able to draw this graph following the same directions. So for instance, we could start from this vertex, and if we followed the arrows, we would end up back where we started here, and we'd still be able to draw the graph. So we've learnt a lot of things here. We've learnt that if we can draw a graph and we end up back where we started, then all the degrees of the graph have to be even, and also it doesn't matter what vertex we start from, we can start anywhere. So this is our case 1, where we end up back where we started. How about the case where we finish at a different vertex to the one we started at? Let's get to where we were before we drew the final line, ending up back where we started. So now in this case, we're here at our penultimate vertex. Let's see what happens if we end up at a different vertex to the one we started at. So we're going to finish our drawing by going up here. Let's label the degrees of the vertices on this graph. So we can see we've got 2 odd degree vertices, and the rest are even. Does this make sense? Well, yes it does, because these are the 2 vertices we started and finished at. So when we started at this vertex, we added 1 to the degree by leaving it. Every time we pass through it on our way, we add 2. So we added 2 when we went through it like this. And then unlike before, we don't finish at it, so we don't have that adding 1 at the end. So the degree of this vertex is going to be an odd number. Similarly for here, this vertex starts off with degree 0, and then when we enter and leave it on our journey, we add 2 to the vertex each time, and then we add 1 at the very end when we finish up at it. So again, this is going to have an odd degree. Whereas all the other vertices, every time we pass through it, we're adding 2 because we're always entering and then leaving it again. So it makes sense, these 2 vertices will always have odd degree, whilst the rest will have even degree. So in this graph, we started at this vertex and ended up here. We could have also done the same trail backwards. We could have started here and ended up there. Could we have started at a different vertex, like this one? Well, actually, if we do that, we're going to get stuck at one of these odd degree vertices. If we're here and we try and draw this, say the first time we pass through this vertex, we're using up 2 of its 3 edges coming out of it, say this one and this one. Then the next time we enter this vertex, we're trying to draw the full graph, so we're going to have to draw this edge at some point. when we come into this vertex, we're going to be trapped because we can't go over any lines, so we're going to be stuck here. So we have to start and finish at the odd vertices. So what we've shown here is that in order for it to be possible that we can draw a graph, or for a graph to be traversible, we need either every vertex to have even degree, or for exactly 2 vertices to have odd degree. It turns out that if this is the case, we will always be able to draw the graph. This is called Euler's theorem.
So in order for a graph to be traversible, we need that either none of the vertices have odd degree, in which case we can start from any vertex and we'll end up back where we started, and this is called an Eulerian cycle. Or we need that there are exactly 2 vertices of odd degree, in which case we can start from either odd vertex and we'll end up at the other vertex of odd degree, and this is called an Eulerian trail. Let's have a look at our first graph to see if this makes sense.
In this square graph, we had every vertex of even degree. So by Euler's theorem, we know that we can traverse the graph and also that we can start from anywhere. So that confirms what we've found. With this graph, however, we've got 4 vertices of odd degree. Now, we've said we need either 0 or 2 vertices to have odd degree to be able to traverse it. So, like we thought, we can't draw this graph. This graph is more interesting. We've got 3 vertices of even degree and 2 of odd degree. So this falls into that category where we've got exactly 2 vertices of odd degree. So this graph we can draw, but we have to start at a vertex of odd degree and we'll finish up at another vertex of odd degree. So that explains why we struggle to draw the graph starting here, but we could draw it when we started here, and I do believe that we ended up at this vertex. So these 3 examples confirm what we've found from our investigation. So if your friend Dave gives you this graph and asks you if you can draw it without taking your pen off the paper, you can secretly count the degree of each vertex, find that they're all even, and be like, no problem, Dave, I can start from any vertex and draw it. Or if Dave gives you this graph and asks if it's traversible, you can be like, why yes it is, Dave. Choose one of these odd vertices, start drawing it, and you'll end up at the other odd vertex, having been along all the lines. And then, to get your own back on Dave, you could create a graph that doesn't have either 0 or 2 odd vertices, like this. This has 4 odd vertices, so it's not traversible. So there's no chance Dave can draw it without taking his pen off the paper.
If you're excited by all this, I recommend you search up the Königsberg Bridge problem for a real-life and historical application of what we've just found.
This brings us to the end of our brief introduction into the wild world of graph theory. Thanks for watching and see you next time.